Just working on some reports.
Yeah.
Yeah, we can't really go into the lab too much, so a lot of the work that we're doing at home is just like writing reports and protocols and getting ready for when we can go back in.
During this time of the pandemic, many of us are stuck at home in our homes or our apartments. But today, on STEM Thing to Talk About, I've got Tricia Longo, who is a scientist for a pharmaceutical company. Welcome to STEM Thing to Talk About. Thanks for coming on the show today. We're happy to have you. Thanks for taking the time.
Yeah, thanks for having me. This is actually my first podcast, so I'm super excited.
Well, lucky you. Could you start off today by introducing yourself and just saying a little bit about what it is that you do in the STEM profession?
I can. So my name is Tricia Longo. I'm a scientist at a company that invents and makes medicine. So the thing that I specifically do is once we make the medicine, we need to test it to make sure that it is what we think it is and it does what we think it does. So, and of course, make sure it's like acceptable to give to people. So I work on making the tests so we can test the product.
And so like the testing of the product now, would that be, now is that testing a product purely on humans, testing on animals? Is it a variety, or how's that work exactly?
So it's none of the above. It's all just we call them characterization tests. So it's to make sure that like the structure of the drug is what we expect it to be. And then my specific thing is really interesting because we test to make sure that it does what we expect it to do. And we use models to do that. So we have, we use cell-based models. So these cells mimic the state of the disease, whatever disease we're trying to treat, and we test the product using that. So in the world of science and research and drug discovery and all that stuff, there are many different kinds of what you would call cell lines. So a cell line is something, a lot of times you can buy them from suppliers, and they're cells from certain organs, or like you can have kidney cells, you can have lung cells, you can have there's like skin cells and muscle cells and all those things out there, and you can either you can insert special kinds of DNA into those cells, so you can manipulate them to act a certain way. So that's what we did to make these models. And then we can measure a response that they put out based on what we give them.
Okay, I gotcha. So they actually are real cells.
Yes,
and
they're real cells.
And you have to manipulate them in a way so that way they act like what exactly? Could you explain that?
So they act like the disease that the medicine is trying to treat. So let's say we'll use some stuff that I did in grad school as an example. So let's say you're a patient who has cystic fibrosis. So what we did, because we couldn't really test anything on actual patients, right? It's grad school. That's not allowed.
Right.
So we got some lung cells, and we didn't actually do any manipulations to these because they had everything we needed just as is. But we tested certain different compounds on them and looked at the response.
Okay, that makes sense. And you, we're going to backtrack just a little bit. You mentioned grad school. So can you explain a little bit about like what your like background is in, and like how you got to be in the position that you're in?
I got a bachelor's degree in bioengineering. And
where'd you get that from?
Syracuse University.
Oh, nice.
Graduated in 2011. And didn't really know what I wanted to do, so I went to grad school, and I got a PhD actually in bioengineering as well.
And was that at
Um,
Syracuse as well?
Also at Syracuse, yeah. My PhD, I got to do some really cool stuff. I just mentioned the one thing, but there was a lot more to it than that. So that was pretty cool. After that, I went and did what's called a postdoc, which is something that a lot of people do after completing their degree, but before going to um, I guess you'd call it the real world, before going to either like an academic position or an industry position. It's just a chance to get some more research experience and maybe publish a couple more papers.
Hmm.
Um, so I did that for a little while. And then I got my first job as a scientist.
And was that at the, what was your first job as a scientist? Is it where you're at now, or is it
It
something
was
different?
at a different company. There um, I was more involved in like the really beginning part of making the medicine, like um, really early stage. Whereas now I focus more on kind of like the end stage of the product.
Okay,
Um,
gotcha.
and I've been at my current job for about 3 years now.
Awesome. So, Trisha, could you start off by saying what it is that led you to going into the STEM field?
Sure. So I kind of always knew I wanted to go into something with math and science, and that's mostly because I really liked science. I was a pretty good student in middle school and high school and got good grades in most of my classes, but the ones that I really liked were the math and science classes. And then I think I was a junior in high school, I had a physics teacher who was at one time a bioengineer. And so
Mm.
that's how I learned about this field. And he kind of encouraged me to pursue that a little bit. So that's really where, how that all happened.
Yeah, very cool. And when it comes to your job, what are some of your, I guess you can choose to do whatever order you want with this. What are some of your favorite things about your job? And then what are your things that you don't like as much about your job?
So one of my favorite things is actually getting to go into the lab and do experiments. It's really cool to like be able to come up with these hypotheses and then be able to test them. Some of the not so fun things are also related to that. So a lot of times, if you have a difficult project, it can take a lot of iterations, a lot of repeating those experiments and hypotheses and not having stuff work, and that can get kind of frustrating. Um, but then in those situations, like in the end when it does work, it's really very worth it, and kind of keeps you going back for more, I guess.
Yeah, absolutely. I mean, that's a big part of the scientific and engineering world is going to be
Mhm.
dealing with those frustrations and troubleshooting and keeping
You
on
have a
moving.
lot of failures.
Yeah, absolutely. Um, Now, so obviously, right now, a big thing in the disease world is the coronavirus. Now, some questions that the students came up with about the coronavirus was um, like, how is the coronavirus different from something like the common cold or the flu?
Mhm. Um, so with things like the common cold and the flu, um, they've been around for a very long time, right? And so, more so the flu, because the common cold doesn't usually tend to cause like hospitalizations or anything.
Hmm.
Um, but the flu can be a pretty dangerous disease. The thing is, healthcare providers, doctors, hospitals, they know that and they expect it and they can plan for it every year.
Hmm.
Um, the thing with coronavirus, and also, sorry, backing up to the flu, there's also a vaccine for it. So,
Hmm.
um, a lot of that potential infection is reduced by people who get the vaccine, which is super helpful.
And I'm
Um,
just going to pause you for a minute. Could you, and then you can go back, but could you explain how a vaccine actually works?
sure, yeah. This is a good question. Person has an immune system, and that's how they fight off all of these different diseases. Immune systems work by kind of tagging those infectious either bacteria or viruses with something called an antibody. And this antibody lets the rest of the immune system know that this is bad, attack this thing. The problem is you need to be exposed to something, either, for simplicity, we'll say either a virus or a bacteria, for your immune system to make these antibodies. And in the case of a vaccine, what that does is it provides a safer version of that infectious material so that your body can recognize it, create the antibodies, and then when you are exposed to it in the future, your immune system can immediately recognize it and attack and destroy it without you getting infected and sick.
Cool. Thanks for explaining that, because I know that's a big question that a lot of people don't totally get how a vaccine works, and I think it's really important to understand. So if you could just continue on, before I interrupted you, you were talking about how the common flu has a vaccine,
Yes.
but in terms of coronavirus.
Right. So this is a brand new coronavirus, at least as far as we're concerned. So they discovered that this existed in, depending on what article you read, around December of this year. And so the flu, people have known about the flu for hundreds of years at this point, right? And so there's just a lot more known about it, whereas this is brand new. No one, like doctors, researchers, haven't really had a chance to study it and learn how it works, create a vaccine, that kind of thing. So I think that's the main difference between coronavirus and the flu. Coronavirus and the common cold is actually caused by a different type of coronavirus.
Really?
Yeah, so coronavirus is a class of virus. It's not a specific one virus.
So the common cold is a type of coronavirus?
I want to be very clear on this.
Yeah,
It is
absolutely.
not it is not the same coronavirus that is causing COVID-19. COVID-19 is caused by something that is completely new, very different from anything that causes the common cold, much more dangerous. And yeah, they're not the same, but they are similar.
Yeah, absolutely.
I don't want to cause any panic here.
No, absolutely. No, we don't want any of that. So can you explain a little bit how the coronavirus actually, how it impacts the body?
Sure. So again, disclaimer, I'm not a doctor here. And this is all very new, so I feel like doctors and researchers are finding out new stuff about this. It seems like every week. But from what I understand, this virus mostly impacts cells in the airway, so in your lungs specifically. And what happens is, so I'll back up a little bit. I mentioned before the virus is basically like a little ball with all these different spikes sticking out of it, right? So in that little ball, it contains genetic material. So think like DNA. This actually is RNA, I think. Anyway, it's genetic material, but the virus doesn't have any of the parts of the cell that allow it to make new cells. So when it enters a person's cell, it kind of hijacks the machinery in that cell, and it makes it make new virus. So you think about it, one cell gets infected by a virus, and it can output hundreds more viruses, which can all go to other cells and infect those cells and make even more virus. And so that goes on and on. And while that's happening, your immune system is trying to create those antibodies, right? Because there's something foreign, but it has to make the antibodies to that thing before it can identify and attack it, which takes some time, right? And so by that time, a lot of your cells have already been infected. There is a pretty big immune response. And since it's mostly happening in the lungs, what can happen in like these severe cases is there's fluid and immune cells and all kinds of stuff that builds up in there and makes it really hard to breathe.
Now, about how long of a period of time do you think it would take for something like a vaccine to be able to come out for like a new virus such as coronavirus?
That's a tough question. I've heard a lot of different things on this. I think the optimistic answer is a year to a year and a half. A lot of people seem to think that's really optimistic and not very likely. Just because this is really hard. As far as I know, researchers have tried to create have tried to create vaccines for other types of coronaviruses in the past, and they haven't been able to. So this is something that's new. It'll take some time, and then once a vaccine is created, it'll have to get made. You can't just invent it in a lab and magically get it to everyone in the world, right? It has to, once it's invented, it has to get mass produced and then distributed out to millions and millions of people.
Yeah, no simple task.
No simple task.
Yeah. If there's some advice that you would give to middle school age students who are interested in pursuing or really interested in like a field like bioengineering, like what would your advice be, I guess, for
them? So my advice would be, so bioengineering is a very broad topic.
Yeah.
So my advice would be pick something specific in there that you think you're interested in. So just to give an example, when I first started down this path, I thought that all bioengineers did was make prosthetic arms or legs or some type of device like that. Yeah. And then, I got to college and learned, yeah, kind of, but that's definitely not it. I think I was really more interested in the biology aspect of it, and so I was kind of lucky in that I was able to find a lab that was doing research I was interested in, and kind of make my own path with it in grad school like that. So I guess, yeah, that would be my advice. Like find what you're interested in and make sure that it fits. Something that I'm seeing that is a challenge, I guess, for me and people that are a little bit older than me, is a lot of things are moving towards computers or robots or something like that. So if there's, and I don't know, if this is something that kids are learning in school now, but if there's any way to learn programming, if you think you want to go into a STEM field, I would highly recommend having at least something related to programming.
That was awesome. Thanks again for coming on, for taking the time to do this. This is great.
Yeah, of course. I hope.
This has been another STEM Thing to Talk About episode. I'm your host, Charles Remlard. I'll see you all again next week.